Good morning, Doctor. My name is Crystal Go, and today I will be presenting my final year project titled Computer Vision-Based AI Inventory Management System for Bicycle Manufacturing. This project was supervised by Dr. Pang. The main purpose of this project is to develop an inventory management system that combines web-based stock management with computer vision detection to improve inventory accuracy and visibility in a bicycle manufacturing warehouse. For today's presentation, I will cover 8 main sessions. First, I will explain the problem background, followed by the project aim and objective. Then, I will discuss the project scope, literature review, and system development methodology. After that, I will present the requirement analysis design, system implementation and testing, and finally the conclusion of the project. The main problem identified in this project is that many small and medium bicycle manufacturers still rely on manual inventory methods. First, manual inventory tracking reduces operational efficiency because staff need to physically count and record stock. Second, there are time lags between actual physical stock changes and system record updates. This means the system quantity may not reflect the real warehouse quantity immediately. Third, manual counting and data entry can cause mistakes. This mistake may lead to differences between physical stock and digital records, which can affect stock planning and production decisions. Next, the aim for this project is to develop a computer vision-based AI inventory management system for bicycle manufacturing. There are 4 objectives in this project. The first objective is to identify the system requirements based on stakeholder needs and current inventory management challenges. The second objective is to design a real-time inventory management system for efficient stock management using computer vision. Third is to implement a system that can detect and recognize bicycle parts to optimize inventory management. Lastly, the last objective is to evaluate the accuracy of product inventory detected by cameras. Next, come to the project scope. First is the case study requirements for this project were provided by Perniagaan Yansan Sdn Bhd. The system is intended for small and medium-sized enterprises in the bicycle manufacturing industry. It was implemented as a web application, and the inventory components included bicycle parts such as frames, wheels, saddles, chains, pedals, flags, and forks. For the computer vision part, the inventory was divided into 3 detection zones. Public dataset from platforms such as RoboFlow were used for initial development, and real warehouse images were also collected when specific parts were not in the public datasets. Lastly, QR code scanning was also used to extract the product numbers and details from part labels. Now come to the literature review part. For the literature review, I first studied the current inventory management issues in SME and also conducted a site visit to understand the real case. The company currently uses auto count to track orders and inventory, but manual counting is still required in the warehouse. Based on the discussion with the warehouse supervisor, Mr. Lee, delays in updating actual stock can cause mismatch between the system record and the real physical stock. Some problems observed include over-ordering due to the updated data, unprocessed returns, and inaccurate stock planning. These findings support the need for a more automated and visual stock monitoring system. Next, I compare different object detection approaches to select the most suitable model for this project. First, one-stage and two-stage detectors were compared. One-stage detectors detect object location and class in one pass, so they are faster and more suitable for real-time use. Two-stage detectors can be accurate, but they are more slower because they first generate region proposals before classifications. Then, I compare YOLO and SSD. Both are one-stage detectors, but YOLO provides a better balance between speed and accuracy, especially for cluttered inventory scenes. Next, for the YOLO version, YOLO V5 was selected instead of YOLO V8 because YOLO V5 is lighter, practical, and more suitable for SME environments with limited hardware resource. Therefore, YOLO V5 was selected as the proposed detection model. For, for the system development methodology, I used a hybrid waterfall agile methodology. The waterfall phase was used at the beginning for requirement gathering, planning, and system design. This was important because the project needed a clear scope, database design, and user interface design before development start. The agile phase was used during development because the computer vision detection and system interface required repeated testing and refinement. For example, the model training, dashboard display, and detection result had to be tested, improved, and tested again until the system became more stable. Next, this system used a 3-tier layered architecture. The first layer is the presentation layer, which was built using React. This is where users interact with the system through pages such as the dashboard, inventory management page, and stock monitoring page. The second layer is the logic layer, which runs on Node.js and Python. This layer handles business logic such as inventory processing, API communication, and computer vision detection. Next, the third layer is the data layer, which uses PostgreSQL to store inventory records, user data, stock levels, transactions, and monitoring records. This architecture helps to keep the system organized, easier to maintain, and more secure because the database is accessed through the logic layer. For data acquisition, I use both public datasets from Loboflow and custom warehouse image collected from Perniagaan Yansan. The target classes used for computer vision training were friend head, wheels, and the QR code on the box. To make the dataset more suitable for real warehouse conditions, images were captured from different angles such as eye level, high angle, and low angle views. Images were also captured from different distance and under different lighting and partial occlusion conditions. After that, the images were annotated using bounding box in RoboFlow. Pre-processing were also applied, including auto-oriented and resizing image to 640 by 640 pixels. Method augmentation such as rotation, shearing, zoom, brightness adjustment, blur, noise, and cutout was used to improve the model's ability to handle different warehouse conditions. Next is come to the evaluation strategy. So the system was evaluated in two main ways. The first evaluation was the computer vision accuracy evaluation. The accuracy was calculated by comparing the AI detected count with the actual manual count. The second evaluation was the usability evaluation, which used Nielsen's 10 usability heuristic. There was 4 evaluators will be included, and the system was tested from both staff and supervisor perspective. The evaluation was conducted using an HP Vitus laptop and an Oppo F9 mobile phone. The materials included task scenarios, a heuristic checklist, and severity rating. Next, this slide shows the main functional requirements of the system. The first function is receiving and stock update. Staff can scan incoming items using QR codes. The system checks the SKU record in the database, and the stock quantity is updated and recorded in the transaction log. The second function is stock monitoring using computer vision. YOLO V5 detects and counts the bicycle parts, and the system compares the camera quantity with the system quantity. If the quantity is different, a mismatch alert is triggered. The third function is outbound operations and stock alerts. When stock is used for production or shipment, the system deducts the quantity from inventory. If the stock becomes low or out of stock, an alert is triggered and the item is shown in the reorder list. Next, the last function is reporting and supervisor actions. Supervisor can view the dashboard, monitor stock movement, perform stock adjustment, and review mismatch cases by marking them as a false alarm or synchronize them to confirm the camera quantity to the inventory system. Next, the non-functional requirements focus on performance, usability, and reliability. For performance, the system should provide a fast response under normal conditions and support real-time inventory updates on the monitoring survey interface. For usability, the interface should be clean, consistent, and easy for new users to learn. Clear icons, label, and navigation were used to reduce confusion. For reliability, the system should remain stable during use and handle brief network issues when possible, including retrying failed requests. This slide shows the entity relationship diagram of the system. The database was designed in third normal form to reduce redundancy and keep the data clean. The main entities entities include items, transactions, and vision alerts. The item table stores inventory item information. The transactions table records stock movements such as inbound, outbound, and adjustment. The vision alerts table store computer vision related monitoring events such as mismatch record. This database design support inventory tracking, transaction history, and camera-based monitoring records. Now we come to the user interface design. This is the dashboard overview of the system. The dashboard was designed to give user a quick summary of the warehouse condition. This slide shows the stock monitoring interface. The monitoring page display the the monitoring page display the video feed, detection bounding box, selected zone, detected SKU, system quantity, camera quantity, and confidence score. Next is the inventory management page. Users can view inventory details such as SKU, item name, location, quantity, safety stock, unit cost, and stock status at here. The patch also supports search, filter, and sort functions, which help users find items more easily. This slide shows the mobile scan interface. The mobile scan interface allows staff to scan QR codes using a smartphone. Staff can choose inbound or outbound mode, and the system will update the stock quantity based on the scanned item. Next, this slide summarizes the system implementation and integration. The system is not only a normal inventory website, but it also connects a computer vision backend for stock monitoring. The process starts from React monitoring page. The page captures frame from the camera roll and sends the frame to the Fast API vision server. Fast API then select the correct YOLO V5 model based on the selected zone. For example, Zone A is for frame detection, Zone B is for wheel detection, and Zone C is for QR code detection. After the detection process, Fast API returns the result to the React front-end. The result includes the detected quantity, bounding box, SKU, and confidence score. The front-end then displays the result on the monitoring page and compare the camera quantity with the system quantity. For inventory data, the system used Node.js and Express as the main backend. This backend manages item records, inbound and outbound transactions, and stock adjustment. All these data are stored in the database. One important design decision is that the camera detection does not directly update the database. If a mismatch happens, the supervisor must review the result first. The supervisor can mark it as a false alarm or synchronize it to the inventory system. This makes the system stable because the AI result is verified before changing the official stock record. So in summary, React is used for the interface, Fast API and YOLO V5 are used for detection, Node.js manage inventory operations, and PostgreSQL store the data. Next, this slide shows the system accuracy evaluation results. For frame detection, the giving accuracy is 100%. For whales, the actual visible count was 38 and the detected count was 36, giving an accuracy of 94.74%. For box and QR code related detection, the actual count was 10 and the detected count was also 10, giving an accuracy of 100%. Overall, this result shows the system was Overall, the results show that the system was able to detect selected bicycle parts with high accuracy under the tested warehouse condition. Based on the evaluator feedback, several strengths were identified. First, the system makes stock counting easier and reduces manual checking effort. Second, the mobile scanning function allows staff to update stock using a smartphone. Next, the evaluators also found that the interface was simple and easy to understand. The clear buttons and color indicators help users quickly identify stock status. Lastly, the vision monitoring function was helpful because it allowed users to notice stock difference earlier. Several weaknesses are also identified during the evaluation. The first weakness is that stacked or broke items affected the camera detection result. When the items were arranged too closely, the camera count might not match the actual stock. Second, some counting results fluctuated, especially when detecting stacked or densely arranged items. This could reduce user confidence in the detection result. Third, the system did a clearer manual checking reminder, so users would know when manual rechecking was required. Other weaknesses include minor lag during large data processing and unclear Excel upload format for first-time users. Based on the weakness, several improvements were suggested. For inventory layout, items should be arranged with clear spacing to reduce broad views. Camera placement should also be adjusted to improve detection accuracy. For count stability, the system can improve count stabilization to reduce quantity flickering. A detection reminder can also be added to show low confidence warnings and guide users to recheck manually. For system performance, large data handling can be optimized to reduce lag. For Excel upload, a simple template can be provided to reduce upload errors. In conclusions, all four project objectives were achieved. The system requirements were identified based on stakeholder needs and current inventory issue. The web-based AI inventory management system was successfully designed and implemented using React, Node.js, PostgreSQL, Fast API, and YOLO V5. The system was also evaluated through camera detection accuracy testing and usability evaluation. However, there are still some limitations. Detection accuracy can be affected when items are stacked, broke, or closely arranged. Also, new product categories or different warehouse layout would require additional data collection and model retraining. So, for future work, the system can be improved by using multi-camera or depth sensing setup to reduce blind spot and occlusions. The dataset can also be expanded with more real warehouse image and synthetic data. That is the end of my presentation, and thank you for your time and attention. That's all from me. Thank you.